What is the main motivation behind the development of the linear attention sequence parallel LASP technique?
The main motivation behind the development of the linear attention sequence parallel LASP technique is to address the significant strain imposed by the growing size of large language models, LLMs, and longer sequence lengths on contemporary GPU hardware. The memory limitations of a single GPU restrict the maximum sequence length of a language model, especially with the increasing size of LLMs. LASP aims to tackle this issue by introducing efficient sequence parallelism on linear transformers, specifically focusing on linear attention models. LASP partitions input sequences into subsequence chunks and distributes them across multiple GPUs, leveraging the benefits of write product kernel tricks in linear attention. This technique maximizes parallelism efficiency and usability, allowing for significantly longer sequence lengths under the same hardware constraints. LASP's design is independent of attention heads partitioning, making it flexible and applicable to models with varying numbers or styles of attention heads. Additionally, LASP incorporates system engineering optimizations such as kernel fusion and KV state caching to enhance execution efficiency, ensuring compatibility with various distributed data parallel training methods.
How does LASP address the issue of memory constraints on a single GPU when training long sequences?
LASP addresses the issue of memory constraints on a single GPU when training long sequences by partitioning the input sequences into multiple subsequence chunks and distributing them across different GPUs. This partitioning helps reduce the large memory footprint associated with activation during the training of long sequences. LASP incorporates a sophisticated communication mechanism based on point-to-point communication for exchanging intermediate states during forward and backward passes among GPUs within a node or across multiple nodes. By efficiently distributing the data chunks and utilizing write product kernel tricks in linear attention, LASP maximizes the utilization of linear attention features. Additionally, LASP implements system engineering optimizations such as kernel fusion and KV state caching to enhance execution efficiency and reduce memory usage. The technique of data sequence hybrid parallelism allows LASP to integrate with data parallelism, further reducing memory constraints on individual GPUs. Overall, LASP's design and optimizations enable it to train long sequences on linear transformers in a distributed environment while mitigating memory constraints on a single GPU.
Explain the difference between intra-chunks and inner chunks in the context of linear attention computation in LASP.
In the context of linear attention computation in LASP, intra-chunks refer to the conventional attention computation within individual subsequence chunks on different GPUs, where each chunk is processed independently without dependencies on other chunks. This allows for parallelized computation within the same GPU or across multiple GPUs within a node. On the other hand, inter-chunks involve leveraging kernel tricks associated with linear attention's write product across different subsequence chunks. This type of computation considers the dependencies between chunks, specifically the impact of previous chunks on the current chunk. Inter-chunks require communication operations, such as point-to-point, P2P communication, to exchange intermediate states like KV activation between GPUs to facilitate the computation of attention across chunks. In summary, intra-chunks focus on independent attention computation within subsequence chunks, while inter-chunks involve coordinated computation across different subsequence chunks by considering dependencies between them and utilizing kernel tricks for efficient linear attention computation.
What are the system engineering optimizations implemented in LASP to improve efficiency on GPU?
The system engineering optimizations implemented in LASP to improve efficiency on GPU include kernel fusion and KV state caching. Kernel fusion is performed in both the intra-chunk and inter-chunk computations, as well as in the updates of KV and DKV. This optimization helps streamline the computations and reduce overhead, enhancing the overall efficiency of LASP on GPU. On the other hand, KV state caching is utilized to store the activation, KV, in the high bandwidth memory, HBM, of the GPU immediately after it is computed in the forward pass. By caching this information, LASP avoids recomputing KV during the backward pass, leading to faster computations and improved efficiency. The size of the KV activation cached in HBM is d times d, which remains constant regardless of the sequence length n, making it a memory-efficient optimization for long sequences. These system engineering optimizations contribute to the enhanced performance and efficiency of LASP in training linear attention-based models on GPU clusters.
Describe the data sequence hybrid parallelism approach proposed in LASP and how it differs from traditional data parallelism.
The data sequence hybrid parallelism approach proposed in LASP involves dividing data along the sequence dimension, allowing for easier integration with data parallelism. LASP partitions input sequences into subsequence chunks, distributing them across different GPUs within a distributed environment. Each GPU trains a subset of subsequences, reducing the memory footprint associated with activation during training of long sequences. Different sequence parallel groups receive different data batches, but within the same group, all data chunks come from the same batch. This hybrid parallelism method combines the benefits of splitting data along both the batch and sequence dimensions, enhancing scalability and memory efficiency. Traditional data parallelism, on the other hand, splits data along the batch dimension only, which can lead to increased memory usage and communication overhead, especially when training large models with long sequences. The data sequence hybrid parallelism approach in LASP optimizes memory usage and communication efficiency by distributing data along the sequence dimension, complementing traditional data parallelism methods for training models with extended input sequences.
How does LASP handle communication between GPUs during the forward pass in linear attention computation?
LASP handles communication between GPUs during the forward pass in linear attention computation by utilizing a sophisticated communication mechanism based on point-to-point, P2P, communication for exchanging intermediate states. This mechanism involves sending and receiving operations between GPUs to transmit the activation states necessary for both intra-chunk and inter-chunk computations. Specifically, in the inter-chunk computation, LASP performs a P2P communication operation called text RECV to pull the activation state KV_T1 from the previous chunk on a different GPU, and then updates the activation state KV_T for subsequent interchunk attention computation. Following this, a text send operation is executed to transmit the updated activation state KV_T to the next chunk on a different GPU. This communication strategy optimizes the exchange of information required for efficient linear attention computation across multiple GPUs in a distributed environment, ensuring that the right product kernel tricks in linear attention are fully leveraged for enhanced parallelism efficiency and usability.
What is the computational complexity of linear attention with causal masking in the transformer architecture?
The computational complexity of linear attention with causal masking in the transformer architecture is OND squared, where n represents the sequence length and d denotes the hidden dimension. This complexity arises from the elimination of the softmax operation in linear attention, which allows for a more efficient calculation of attention scores without the quadratic time complexity relative to the input sequence length n. Linear attention achieves this by leveraging the right product kernel tricks, which facilitate recurrent prediction and efficient inference by updating the key-value pairs without the need to compute the entire attention matrix. Despite the advantages of linear complexity in terms of computational efficiency and memory optimization, the computational and memory utilization on a single GPU increases proportionally as the sequence length n grows, potentially leading to memory constraints on a single GPU, especially for exceptionally long sequences.
Explain the communication analysis, comparing LASP with Megatron LM and deep speed in terms of communication volume.
LASP achieves lower theoretical communication volume compared to Megatron LM and deep speed due to its efficient communication design. In LASP, the communication volume for the forward pass is determined by BD-2 per hour, where B is the batch size and H is the number of heads. In contrast, Megatron LM utilizes all gather operations twice and a reduce scatter operation, resulting in a communication volume of 2 BND plus 4 BND, T. Deep speed uses all-to-all collective communication operations, leading to a communication volume of 4 BND, T. LASP's communication volume is not affected by changes in sequence length N or subsequence length C, making it advantageous for long sequence parallelism across large GPU clusters. LASP's efficient communication mechanism allows for the exchange of linear attention intermediate states, resulting in enhanced throughput and performance compared to Megatron LM and deep speed.
What are the key findings from the experiments conducted with LASP on linear attention-based models TNL and linear transformer?
The key findings from the experiments conducted with LASP on linear attention-based models TNL and linear transformer are as follows. 1. LASP enables the scaling of sequence length up to 4096K using the FSDP backend and 2048K with the DDP backend on a TNL model with 1B parameters on 128 GPUs. This scalability allows for a linear increase in the maximum sequence length capacity proportional to the number of GPUs used. 2. LASP demonstrates consistent scalability performance under both the FSDP and DDP backends, maintaining a high throughput level even with more GPUs used. 3. LASP outperforms existing SP methods like DeepSpeed Ulysses and Megatron by 38% and 136% in terms of throughput at 256K sequence length on the 1B model, with the performance gap widening as the sequence length increases. 4. System optimizations such as kernel fusion and KV state caching in LASP enable it to support the longest sequence lengths within the same cluster, achieving 2048K for the 1B model and 512K for the 7B model. 5. LASP does not negatively affect model convergence, as demonstrated by consistent loss values across various DDP backends for both TNL and linear transformer models during training on the pile corpus over 50K steps. 6. Ablation experiments comparing activation checkpointing AC and LASP show that LASP significantly reduces activation memory usage per GPU, allowing for remarkable increases in maximum sequence lengths while maintaining throughput, with the scaling performance of LASP being directly proportional to the number of GPUs used. Overall, LASP proves to be a highly efficient and scalable technique for training linear attention-based models, offering significant improvements in throughput, scalability, and memory optimization compared to existing sequence parallelism methods.
How does LASP achieve linear scalability in terms of sequence length with the number of GPUs used?
LASP achieves linear scalability in terms of sequence length with the number of GPUs used by partitioning the input sequences into multiple subsequence chunks and distributing them across different GPUs. Each GPU trains a subset of subsequences, reducing the memory footprint associated with activation during training of long sequences. Communication operations are employed between GPUs to transmit intermediate states, allowing the final trained model to assimilate knowledge from the entire long sequences. LASP evenly partitions the input data into chunks, with the sequence parallel size being divisible by the distributed world size. This configuration ensures that the input data is split along both the batch and sequence dimensions, enabling a type of hybrid parallelism called data sequence hybrid parallelism. LASP's design allows for a linear increase in the maximum sequence length capacity, directly proportional to the number of GPUs used, resulting in linear scalability.